Hi, here's a little guide to Snell's law. So, from our idea of refraction, we know that if we take two different densities, let's take air into a plastic block, back into air. If we hit at an angle, and we mark off against this normal, the normal is the angle we measure from, then we see that light refracts, it bends. And we can measure these two angles. This one we will call theta incident, and this one we will call theta refracted. And so now we have two angles, theta incident and theta refracted. And what Snell's law does is it allows you to mathematically predict what each of those angles will be by knowing something about the material that the light is travelling through. And we know light travels at 300 million meters per second, but that's only true for a vacuum. When it goes through air, it goes a lot slower, and through plastic even slower. And we can put a number to the amount of slowing, and we call that the refractive index, N. And that's spelled refractive index. And for air, it is 1, so we say N incident 1, and for plastic it's about 1.4 to 1.6. It alters, and also as you measure this you'll get slightly different results. And from that we can derive Snell's law, which says quite simply refractive index times sine theta incident is equal to N refracted sine theta refracted. And there's loads of ways you can rearrange this. We've at the end of the day got an equation that's purely of the form A, B, C, and D. And so you might see Snell's law written in lots of different ways. If we're taking it in the air, then Ni is 1. You might see it written out as Nr, the refractive index, is sine, let me get this right, sine theta incident over sine theta refracted. One way of rearranging it, because that would be 0. Another way of seeing it rearranged, and it's the way I was taught, is you might have sine theta incident over sine theta refracted is equal to N, little n, N refracted over N incident. And if you times those back out, you put that over there, and you take that and put that over there, you end up with that top box again. Okay, so be a bit plastic in your thinking here. I'm giving you it as the top row there, but from that you can rearrange it to look however you want to see fit. So, question time. Let's try one. We'll go between two liquids. We'll go between water, refractive index of 1.2, to the air, refractive index of 1. It's going in at an angle like such, and then it's going, now I've got to get this the right way, it's going at that angle there. Yeah. We've got theta, and we're going to go this way. Theta incident is 20 degrees. Theta refracted, I'm doing this off the top of my head, so forgive me if I go completely wrong with this, 65 degrees. No. Take that off. Question is, can you find theta refractive? So rearrange it, see if you can find that angle.